We're going to do partial derivatives today. Big day for you. Big day. Now, don't be fooled by the name. The word partial is very misleading because it sounds like, oh, well, I don't have to do it all the way. I'll just, kind of sort of do it half-heartedly. No, 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 no. That's not what the word partial means, okay? You'll see sort of why they call it that. I wish they had called it something else, but I wasn't around when they named these. So it wasn't my call. So we're going to look at partial derivatives today. And basically that is the name that they give when you're taking derivatives to functions of more than one variable, as we'll soon find out. So let's do sort of the background anytime you do take a derivative, and you know this already from Calculus 1. So what happens, how does a function get affected by changing one of the variable, if you're doing a function of a single variable? But now that we have a function of more than one variable, suppose that you change one of the variables, make it kind of move around a little bit, but keep the other guys fixed. So that's basically what we're going to put in the answer here. You're going to hold all variables constant except one, the one that you're interested in looking at, and then vary that one and examine the results. And this process is known as partial differentiation. So you can fill in the blank there, partial differentiation. And the result is referred to as, this is going to be long, the partial derivative of f, and then in parentheses, w period r period t period. That stands for with respect to in mathematics. I don't make this up. I just report it. With respect to the chosen independent variable. Well, how do you know which one's chosen? You'll know. We're going to have special notation for it. So this is known as the partial derivative of f, where f is your function, with respect to the chosen independent variable. So let's look at the official definition for the derivative of a function of two variables. If z gives you fxy, there's your function f of x and y, function of two variables, then the first partial derivatives, this is what we're talking about, the first partial derivatives of f with respect to x and y are the functions, so your derivatives are themselves functions, okay? And you know this already from Calc 1. One of them is going to be called f subscript x. The other one is going to be f subscript y. Yeah, there's two of them. You got two first derivatives. Really? Yeah, why do you have two derivatives? One for each of these independent variables, one for x and one for y. So the one for x, we use that notation, the subscript notation, subscript x. And I'm going to give you the limit definition. This is x comma y. It's the limit as delta x goes to 0 of f evaluated at x plus delta x, comma, y minus f of xy all over delta x. The other first partial derivative is the derivative of f with respect to y, using the notation f subscript y of xy, because it's also its own function. And that's also given by the limit, only this time you take the limit as delta y goes to 0, of f x comma y plus delta y minus f x comma y all over delta y. Okay, now when you're taking the first partial of f with respect to x, what you do is you're going to put on a special set of glasses. Okay, I'll put a pair of glasses here. You'll put on a special set of glasses where when you look through them, it looks like y is constant. You treat y as a constant when you're taking the derivative of f with respect to x. Now, when you're taking the derivative of f with respect to y, you put on a different set of glasses. These are different color here. And you look through these glasses and it appears, at least temporarily, that x is being held constant. So you treat x as the constant. Now, if you still don't get my glasses reference, don't worry. When I get to the example pretty soon, we're going to put on our glasses. You've heard of looking through rose-colored glasses. Kind of going to be like that. Okay. So when you take fx, you consider y to be constant and you differentiate with respect to x. When you find the other first partial, fy, you consider x a constant and differentiate with respect to y. Okay? Now, good news, we are not going to find limits using, derivatives using the limit definition. It's kind of challenging, so we're going to let it go. We're going to just do some derivative rules instead, okay? So using the limit definition is a challenge, so we're not going to use the limit definition, okay? Good news. Now, before we do our very first example, I want to review a couple of easy peasy calculus 1 derivative rules that you already know, but I just want to remind you of them because it's helpful. So one calculus 1 review here is called the constant rule. Do you remember if you're taking d dx, for example, the derivative with respect to x, of just a pure constant, c, where c could be your favorite number, 2, -57, 0.5, some constant. What is the derivative of just a constant? Anybody know?
0.
Yes.
0.
Oh, thank you. Okay, you guys all know that one. You're graduates of Calc 1. Good for you. Now, what if you're taking the derivative with respect to x, say, of not just a pure number, but a pure number multiplied by some other junk that might have x's in it? You probably remember that the constant c just kind of goes along for the ride. So he's still there. He doesn't disappear. And he just multiplies with the derivative of whatever the other rest of that expression was. And that's known as the constant multiple rule, okay? You've seen both of these in a Calc 1 class, and I'm sure you're familiar. So now, keeping those in the back of your mind, we're going to get the first partials, both of them, fx and fy, for this function. Z equals fxy, 3x minus x squared y squared plus 2x cubed y. So first up, we're going to find fx. When you find the derivative of a function with respect to x, and it's a function of 2 variables, you're going to put on a special set of glasses here. Here's your special set of glasses. And you're going to hold y constant. That means temporarily, every time you see the variable y, treat it as if it's a number, like 2 or something like that. Okay, treat it as if it's a number. Okay, keeping that in mind, here we go. What is the derivative of 3x with respect to x? That's not hard, you all know that one.
3.
Yeah, 3. Minus, because there's a minus next. Now we're going to take the derivative of x squared times y squared with respect to x. Now remember, y looks like it's a constant. So that means the y squared is just some constant multiple. So just copy it down for the ride and multiply that y squared, which you're treating as a constant, times the derivative of x squared with respect to x. And we all know that the derivative of x squared with respect to x is simply 2x. And we're done with that term. Plus, now the very last term, the derivative of 2x cubed y with respect to x. So the 2 and the y together just look like some constant multiple. So copy it down for the right, and you're going to multiply that constant multiple with the derivative of x cubed with respect to x, which is 3x squared. And then clean this up a little bit because I like to see your coefficients in front. So I'd like to see it. And by the way, I'll use the notation. Since fx is itself a function of two variables, let's kind of use the notation here, fx with the parentheses x comma y. So anybody looking at that goes, oh yeah, even the partial derivative fx is a function of x and y. So he's going to be equal to 3 minus 2xy squared plus, and then the last term, 2 times 3 is 6. And it's customary to write your x's and y's in order, alphabetical order. And we're done. There is your first partial of f with respect to x. Yay! Now let's find the first partial of f with respect to y. So you're going to take off the old set of glasses, but you're going to put a new set on. This new set of glasses, woo! Every time you look through them, it's going to appear that x is constant. So x's are treated like the number 2 or something.
So
Okay.
negative 2yx squared plus 2x cubed.
Okay, well, we're going to go a little slower than that. So thanks for going fast, Lupe, but bear with me. So I'm going to start over here. I'm going to take the derivative of 3x with respect to y. So when I'm taking derivatives with respect to y, x looks like a pure number. So 3x just looks like a pure number sitting all by itself. And what do we know about the derivative of a pure number all by itself? The derivative is
0.
0. So that first term's derivative is 0. Yay. And then the second, we got the minus there. Taking the derivative of x squared y squared with respect to y, x squared is a constant multiple. Copy it down and multiply that by the derivative of y squared with respect to y, which is 2y. Plus, and then finally, what is the derivative of 2x cubed times y with respect to y? Just
Would it be
2x
2x cubed? Yeah.
Yeah, just the 2x cubed. And then clean this up a little bit because you don't need to write the 0. We can just write negative 2x squared y plus 2x cubed. And we're done. And that's the other first partial. Pretty cool, huh?
So I'm kind of confused about the 0. So it's 3x.
Okay, but we were taking the derivative of 3x with respect to y because we were taking the first partial with respect to y, which means you've got this special set of glasses over your eyeballs. And when you look through that special set of glasses, all of the x's appear as a constant for that moment when you're taking that derivative with respect to y.
Okay, I got it. That makes sense.
So then 3x just looks like a pure number. Yeah? So
Yeah.
let's do some alternative notation. You may see partial derivatives denoted in a variety of ways, and you need to be comfortable with all of the varieties because on a quiz or exam or homework, they may be asking you for a partial, but if you're not comfortable or familiar with all the different ways, you might be going, oh, what's this? So we already looked at the subscript notation way. Fx is how you say I want the partial with respect to x. What's another way? Now, another way is just fx, where they're doing more function notation, where they have the parentheses x comma y. That's same thing. Now I'm going to introduce you to the D notation. You may see it as df over dx, but this is not the regular D that you saw in a Calc 1 or Calc 2 class. These D's have what's called melted stems. Their stem is curvy. So not to be confused with a straight stem D. A straight stem D is not going away because we'll see those show up later this week. But the curvy stem, this is a curvy stem D, is how we denote partial derivatives from now on and forever. And if I see incorrect written Ds on your handwritten work, you know, I'm going to take a point off here and there for yucky notation, because yes, it matters. And then another way you may see the first partial of X written is the melted D, the curvy stem there, fxy dx. And then sometimes, since Z is often used to denote the function fxy, you may see the first partial of Z with respect to X. That's also legit. Okay, now I'll put a little border here. What if they asked you to evaluate your first partial at a particular point? They may go like this, fx and then parentheses a comma b, where a and b are actually some fixed numbers. Or another way they may denote that you need to go evaluate your partial at some point. They'll go df dx, and then they'll have a vertical bar. And at the bottom of the vertical bar, using subscript notation, so it's tinier font, the point, the ordered pair, a comma b. And that's basically just saying, hey, plug it in. Plug in the point AB. Okay, now let's do the same for the other partial, f with respect to y. You may see it denoted f parentheses x comma y, or df dy, where the d has a curvy stem, or df x comma y over dy, or dz dy. And then if they ask you to evaluate this first partial at some particular point, they'll give it like this, or they'll use that more differential notation, df dy, vertical bar, and evaluate at the point AB. Okay, now let's do some examples. And then you're going to get a chance to try one on your own. And I have kind of a hard one just to mess with your head. We'll find out. Okay, example 2. Let's find fx and fy, the first partials, for this function. Fxy is equal to x e to the x squared y power. And then once we have those first partials, let's evaluate both of them at this particular point P with coordinates 1, ln 2. Okay, so let's find fx first. Keep in mind, when you find fx, you're going to hold y constant, just temporarily, okay? Just temporarily. You're treating y as a pure number. Now, I want you to notice something. This is a hard problem. Because we have the product of x with the exponential that also has x, we are going to need the product rule. And so you know we're going to have to go like f prime g plus g prime f, like that. Where the f would be the first factor. That'll be just the x. And the g will be the exponential, the e to the x squared y power. And you have to remember how to take derivatives of exponentials. So just a little quick review from Calculus 1. When they ask you to take the derivative of e to the u, it's e to the u times u prime. So if we're doing a first partial with respect to x, the derivative of an exponential will be e to the u, and the u prime will be taking the derivative with respect to x. Okay, so here we go. Let's do this slowly. The derivative of the first factor, x, with respect to x. What do you think that is? Easy, right?
1.
So 1 times the exponential plus, okay, now we're going to do the g prime. So that means you're going to take the derivative of e to the x squared y with respect to x. So it's going to be e to the x squared y. There's your e to the u times the derivative of x squared y with respect to x. And that means the y goes along for the ride, and you multiply the y with the derivative of x squared with respect to x. So that's 2xy. And then times your original x factor. So this is fx right here, and you probably want to clean this up. I like to see the polynomial factors in front of your exponential. That's customary, and so please follow custom. And you could factor a common factor of e to the x squared y out of here if you wanted to make it more pretty. I'm not going to. If I were to evaluate this at the point 1 ln 2, then I would simply direct substitute e to the 1 squared times ln 2 plus 2 times 1 squared times ln 2 times e to the 1 squared times ln 2. Now, I wouldn't give you full credit for this. Recall, there's a really handy pre-calc thing that you learned when you studied exponentials. E to the ln of a is equal to a. Do you remember this handy fact? I'll put stars
Yes.
by it. So what is e to the ln 2 simplify to?
2.
Good, very good. So this is going to be a 2, and so then 2 times 2 is 4. And so when I evaluate that first partial at the point with coordinates 1 ln 2, I get this weird number, 2 plus 4 ln 2. Okay, that's just a nice number. It's not bad. Brilliant. Let's go get the other first partial. Yay! And I ran out of room because I never leave enough room for myself. What can I say? All right, so if we go get Fy now, that means we're going to put on our other set of glasses that treats x as a constant, okay? So we're trying to take the derivative of x e to the x squared y with respect to y. So we're going to go Fy, and that means we're going to hold x constant. Do we need the product rule this time? Anybody want to courageously venture a guess?
No.
Correct. No, we don't. Because this x that's sitting in front of the exponential, you're just treating that as a constant. He's like a 2 or something. So you're just going to go, oh, if I take the derivative of this expression with respect to y, x is just a constant, so just multiply him with the derivative of the exponential with respect to y now. So you're still going to use the exponential rule for derivatives. E to the u, e to the x squared y, times
Oh, okay. I see.
derivative
I
of
see
x
what's going
squared
on.
y with respect to y. So what is the derivative of x squared
It's
y?
gonna be x cubed to the x cubed y power. I mean, e to the x cubed y power. I mean, x squared y power.
Oh dear.
2xy.
Oh dear. Oh my goodness. No.
No.
Let's do an aside. What if I said take the derivative with respect to y of x squared y? Let's just do that only. Just go with me on it. Remember, x squared is treated as a constant, so you just copy him down and he goes along for the ride. Then what is the derivative of y with respect to y?
1.
Thank you. So when I do the exponential rule with respect to y on the exponential, here's the e to the u portion, and then times u prime. The u prime is
I'm
simply
sorry. Yeah,
going to
that's
be
what I was
x
saying.
squared only.
That's what I've
And-
been meaning to say. That's what I've been trying to say this whole time.
Okay.
I meant to say
There you go. Finish off this problem by multiplying the factors of x together, and we're going to get x cubed e to the x squared y as our first partial with respect to y. And now that we need to evaluate that at the point with coordinates 1 ln 2. Okay, now you're just going to do direct sub. So 1 cubed e to the 1 squared times ln 2. What's e to the ln 2?
2.
Just 2.
Just 2. So when we evaluated that partial at that point with the special coordinates, we just get the number 2. Okay, and we're done with this problem. This problem is a little involved. And it involved lots of knowledge of derivatives while we were getting those partial derivatives. Now let's talk about what does it mean with these partial derivatives. Well, let's back up a little bit. When you took Calculus 1, what did it mean when you got the derivative at a point? So quick Calc 1 review. What's the geometric interpretation of f prime of x? Yeah, slope. So here's the question, and then here's the answer, slope. Because you remember when you took Calc 1, if you had some graph of y equals f of x, and they said, okay, here at the point 3, just say, they wanted the equation of the tangent line, you had to get the slope of the tangent line, and that's going to be the derivative evaluated at that point. So you already know a little bit about geometric interpretations of derivatives. So let's go and figure out what it is for us. For a function of two variables, remember that the graph of a function of two variables is the surface. So this surface is given by z equals f x comma y. That's that red, a portion of the surface anyway. Okay, and what they're doing here is they're picking a point on the surface. It's an ordered triple. And if you were standing on that surface, pretend it's like a mountain, and you were looking in the direction of the positive x-axis, the slope of the mountain in the direction of the positive x-axis would be df dx, your first partial of f with respect to x. That's pretty cool. And then this other picture over here, which I've sadly written over, you've got your surface here, so that's the red. You can think of it as a portion of the mountaintop. Your surface is given by the equation z equals f x comma y. That's the graph of it. And here's you standing up here with your skis, okay? And if you face in the direction of the positive y-axis, df dy, the first partial with respect to y, is going to get you the slope in the positive y-axis direction. Pretty nice, huh? Now, if you're a thinking student, you might be thinking, well, what if I don't want to ski in the direction of the positive x or the positive y-axis? I'm kind of wanting to ski maybe right in between those two axes. What's the slope going, diagonally in between? And the answer to that is wait till Friday's lecture. You're not ready. But it's a good question, and it's a legitimate question, but we're not going to answer it today. So here we go. Let's do a couple of finding slopes in x and y directions now that you know. And so finding the slope in the x direction is simply obtained by finding fx, and finding in the y direction means we better go get fy. So this function they're giving us is a pretty easy function because it's super easy to get the partials of, since all of the terms don't have both x's and y's in it. So if we're going to go get fx, also known as df dx, you're going to hold y constant, which means you're going to treat y as a pure number, just for the moment. So let's take the partial of negative x squared over 2 with respect to x. And that's just the same as you would in calculus 1 because there's no factor of y in there. Yeah. And I claim it would just be negative x after you reduce it to lowest terms. So, I mean, if you want to go in slow motion, we could go negative 2x over 2. What about the derivative of minus y squared with respect to x? Anybody want to guess what that would be?
0.
Good. 0, because y squared is a pure number. How about the 25/8?
0.
0.
So we have negative x. And then when we, this is a function of two variables only. So why did they give us the third coordinate? They're trying to mess with you, but that actually is the coordinate on the surface. But these partials are functions of two variables only. So you only have to worry about the x and the y coordinate given there. And then when you use direct sub, you're just going to get minus a half. So the slope, if you were facing in the positive x-axis direction of this surface, would be a negative a half. Now, what does it mean when the slope is negative? It means if you were a skier and you were looking in the positive x-axis direction, you could actually ski down the hill. So this is perfect skiing conditions. Perfect ski conditions. Okay. What if you got a positive a half? it would not be good for skiing. Well, why not? Because it would be slightly uphill and it's kind of hard to ski uphill. Okay, let's get the other partial, Fy, which you can also denote the FDY with these curvy stems. Now you're going to put on your other set of glasses and you're going to hold x constant. Ooh. So when you take the derivative of this function all over again, but with respect to y, what is the derivative of the first term, negative x squared over 2, with respect to y?
0.
Mm-hmm. Derivative of minus y squared with respect to y is minus 2y, and then of course the 25 is 0. So we're just going to get negative 2y. And then if we evaluate this at the point with x and y coordinates a half 1, we're just going to get negative 2 times 1, which is negative 2. Also perfect skiing conditions. In fact, if you're a hotshot skier, you probably would prefer skiing in the direction of the y-axis because it's going to be steeper than skiing in the positive x-axis direction. Okay? And we're done with part A. So now let's look at a new function. Suppose this represented some mountain surface. What are the slopes in the x and y directions for this surface? And here you're going to need the chain rule. That's why I put it in here, just so you can get some comfort with those old Calc 1 rules. When you're taking fx, you're going to hold y constant. So just temporarily, y looks like a pure number. Of course, the derivative of 1 is 0, and then you got a minus there. And when you take the derivative of x minus 1, the quantity squared, using the chain rule, it's 2 times the quantity x minus 1 to the 1 times the derivative of x minus 1 with respect to x. But that's just going to be 1. And then the rest of it is going to be a 0 because the rest of that problem just has, you know, y's and 2's. It looks like a pure number. So we're done. So this is, if I clean it up a little bit, looks like that, negative 2 times the quantity x minus 1. And if we evaluate this partial derivative with respect to x at the point with coordinates 1, 2, and we're just going to plug in x equals 1 here since we don't have any y's, I get 0. Can we have a slope be 0? Sure. You remember from calculus 1, what happened when your slope was 0? Does anybody remember?
A local max.
Mm-hmm. Mm-hmm. Or you would have had a local min, right? One or the other?
Yeah.
One or the other, yeah. Okay, but wait a minute. Do we have the Fy equal to 0 also? So let's go get the other first partial. Hang on a minute. We would need both Fx and Fy to be equal to 0 to get a max or a min in 3D. So here, put on your other set of glasses and hold x as constant. And when you get the first partial of f with respect to y, okay, what happens here? Well, the derivative of 1 with respect to y is 0. The derivative of x minus 1 squared with respect to y is 0. So you just got a big fat 0 there. Then the last term, you're going to use your chain rule. And this is going to be negative 2 quantity y minus 2 to the 1 times the derivative of y minus 2 with respect to y, which is just 1. And then evaluate this partial derivative at the point 1, 2, and we'll substitute y equals 2 here. And I get also a 0. So when this happens, when you get both of your first partials equal to 0, you do have a relative max or a relative min. Well, which one is it? How do you know? Stick around. You have to do a lot extra to figure out which one it is, or neither. So you're not ready yet. But what would it look like to have a local min or max? Well, if your surface, if we're going to talk about surfaces being mountains again, it would mean, for example, you know, your mountain here, if this were a surface, would have a max there, or it would be the bottom of a valley. So one or the other, would be happening there if you had your local max or min in 3D. Okay. All right, it is your turn. So you're going to get a shot at finding partials. So you're going to find the slopes in the X and Y directions. That's just basically code for go get fx and go get fy. And then when you're done, evaluate it at that point. Okay, so that is the plan. So I wanted to show you a picture of this surface here because it's kind of freaky. Look at that. Isn't that wild? Whoa, yikes. And notice it's got a lot of asymptotes in it. And that's because in your function, you know, you had y and x cubed in denominators, which means, you know, you don't want denominators equaling 0. Whoa, that's making me dizzy. Sorry, let me switch to candy stripes. Ooh, pretty. So it's kind of a cool surface. Anyway, I digress. So hopefully you made some progress using your power rule. So if you took my hint to heart, what you did is you first rewrote your function. You didn't take derivatives yet. You've got the 1/3 x squared y to the -1 plus 4x to the -3 y squared. Now, let's go get those first partials. So fx. So remember, you're going to hold y constant and just differentiate with respect to x, the usual way. So with your first term, the 1/3 and the y to the -1, I'm just going to copy them down because those get treated as constant multiples. And you multiply that by the derivative of x squared, which is just 2x. And I'll clean this up later because I want your final answer to have positive exponents only. And it's easier to plug stuff in anyways when you have that. The second term, the 4 and the y squared are treated as constant multiples. And you multiply by the derivative of x to the -3. The derivative of x to the -3 using the power rule is -3x to the -4. Yep. And I'm going to rewrite both of these terms with positive exponents only. So the first term looks like 2x over 3y. And then the second term, after I get done multiplying the 4 and the -3 together, I'll get -12 y squared divided by x to the 4th power. So that's fx. If I evaluate fx at the x and y coordinates to get given, you can ignore the z coordinate because these two partials are only functions of x and y. Well, why'd they give the z coordinate? Who cares? Because this ordered triple is the actual location in 3D on the surface itself. So somewhere on this surface is the point, who knows where, 6, -1, -64, 7/54. That point, and then we're facing in the x-axis direction right now and trying to figure out the slope. And that's found by substituting in the coordinates, the x and y coordinates, that is, to this point. So after you substitute this in there, whoa, I get, what do I get? 12 over -3 minus 12 over 6 to the 4th, which I think is 1296. And then you can reduce the first term, of course, to -4. But then what is this? I get -4 minus 1 over 108, which completely simplifies to this yucky number. I know, -433 over 108. Okay. Did anybody get that for your fx? That's your slope in the positive x direction.
I got it.
Yay! Success. All right, let's get fy. So now when we go get fy, you're going to put on a different set of glasses.
Oh, what do you know? It's actually right.
X constant. Okay, you got it right. All right. So now you're going to take the derivative with respect to y, and you're going to treat x as a constant. So go back to the original function here, the one that I rewrote. And when you look at that first term and you take the derivative with respect to y. So the 1/3 and the x squared are just copied down because you treat that as a constant multiple. And the derivative of y to the -1 using the power rule is -1 times y to the -2. Okay. Plus, and then the second term, I'm going to just copy down the 4 and the x to the -3 factors. Those are just constant multiples. and multiply by the derivative of y squared with respect to y. And that's easy because that's just 2y. And let's rewrite this using positive exponents only just to make it look pretty. And it make it easier to substitute in the coordinates of the point. So the first term is negative x squared over 3y squared. And the second term looks like 8y divided by x to the positive 3. And there's your fy. And when I evaluate fy with the coordinates 6, negative 1, using substitution here, what do I get? Oh my goodness. Oops, I forgot. This should be 6 squared. Sorry, my bad. I'm doing it backwards. Sorry. So that should be what? Negative 36 over 3 for the first term, plus negative 8 over, I think it's 216. And then add these together and use your calculator. Use your frac command on the calculator. Anybody know about the frac command? Anybody want me to do the frac command that doesn't know? Let me know in the chat. I'll do it. Somebody want to see the frac command? Say yes. No.
Yeah, show us, please.
Oh, okay. Want me to show you? Fantastic. All right. Let me get up my calculator. I'll pull it up. What the heck is the frac command? This is like very powerful. I use my frac command all the time. I like to frac stuff. What the heck do I mean when I want to frac it? Okay. So as an example, let's just do like negative 36 divided by 3. I know that what that reduces to. And then minus 8 divided by 216. And then I hit enter and I get the decimal value, but I don't want the decimal value. That's an approximation. I want the exact value. Uh-oh. So you go over here to your calculator and hit the math button. And the very first menu selection in the math button is the math menu, and it's frac, and that stands for fraction. So that's the one I want. It's already chosen. So I'm just going to hit enter and then hit enter one more time to push the calculator into giving you the frac or the fraction for the decimal. Okay. Now, folks, this should only work if your decimal actually corresponds to a rational number, because there are decimal numbers out there. For example, pi 3.14, blah, blah, blah. It's a non-terminating, non-repeating decimal that does not have a corresponding frac. And some people would go, well, yeah, but it's 22/7. No, that's an approximation. That's not exact. Okay, so I know there's some TI calculators out there, unfortunately, that give the closest fraction to an irrational number, and I wish they wouldn't, because I will mark you wrong. That's not cool. Definitely not cool. Okay. So if you want more private lessons with this or you have questions, see me after class or during office hour. I'd like to keep moving. Let's take a look at the next example, because it's a little bit harder now. Woo! What do you mean? Well, now they're asking us to take some partials for functions of 3 variables. So let me, before I even do example 4, let me cue this up. You see, it matters how many independent variables you have in your function. What do I mean by it matters? Well, if you have a function of 2 variables only, what are you saying? Here's a little schematic, and we're going to do more schematics later. But you got your z, and you've got, z is a function of x and y. So that means you're going to have 2 partials. You're going to basically have an fx, and you're going to have an fy. 2 of them. What if you have a function of 3 variables, x, y, and z, just say, okay? How many first partials do you think you're going to have here? How many kids, if you will? You're going to have 3, because you have 1 first partial that corresponds to each of your independent variables. So if you had a function of 4 variables, just say, how many first partials total do you think you'd have? I'll just leave that hanging.
Or
Thank you. 4. So they're not asking us to find all the kids here. They're just asking us to find DFDZ only, even though there are 2 other partials. There's a DFDX and there also is a DFDY, but they want us to only find DFDZ. Okay, fine. So when you're going to find DFDZ, that means you need to put on a very special set of glasses, because you need to hold both of the other variables, the X and Y, constant. So what does that mean? This set of glasses is super powerful because it's treating both X and Y as constants now and taking derivatives with respect to Z. Ooh. So what would the first term's derivative, XY, be if you were taking the derivative with respect to Z?
zero.
Good. Why?
There's no Z's. The first thing.
Good. There's no Z in there, so that looks like a pure number. And the derivative of pure number is 0. Plus the derivative of y, z squared. Well, y is a constant multiple. Copy it down and multiply that by the derivative of z squared with respect to z, which is 2z, plus the derivative of xz with respect to z. That's x times the derivative of z with respect to z, which is just 1. So if I clean this up a little bit, it's 2yz plus x, and I'm done. That's the derivative with respect to z. Let's do another one that's harder. Suppose they gave us another function of 3 variables, which would have 3 partials total, but they only want 1 out of the 3. They want DFDZ again. So you're going to hold both x and y constant. Now, do you see why this is harder? I need to take the derivative of z times sine of xy squared plus 2z with respect to z. So I'm going to need the product rule. And I'm really into the product rule. You'll see. It's definitely going to be on your midterm. Oh, yeah. Okay. So I'm going to first take the derivative of z with respect to z. That's just 1. Times the sine function. So I'm just going to copy the sine function down. Plus the derivative of the sine function with respect to z times z. So we're going to have some junk, and then of course times z way out here. So the derivative of sine is cos. So you're going to have cos of xy squared plus 2z times the derivative of that argument with respect to z. Well, the derivative of xy squared with respect to z is 0, plus the derivative of 2z with respect to z is just 2. And now you can clean this up. So DFDZ is going to equal this sine function, sine xy squared plus 2z, plus, and then it's customary to put your coefficients and any polynomial factors in front of your trig function factors, please. Otherwise, I'll dock you a point for yuckiness. So here is your DFDZ right here. Wow, that's pretty beautiful. Wow. Now let's do a function of 4 variables, which would need 5 dimensions if you had to see the graph, but nobody's asking us for the graph. That's good. They just want a partial derivative. What partial derivative? DFDW. So when we get DFDW, that means we're going to have to put on a real powerful set of glasses, because we're going to hold x, y, and z all constant. And we'll take the derivative with respect to w. So what I'm going to do first, just to make this problem easier, is I'm going to rewrite the function itself, because I can. Because I want to do the rewrite so I can do the power rule. I could use the quotient rule, but that's overkill for this problem. So this is a rewrite of the original function. I haven't taken a derivative yet. Now let's take the partial of f with respect to w. So The x plus y plus z is just a constant multiple, so copy it down, times the derivative of w to the -1 power with respect to w, -1 w to the -2. And if I were to rewrite this to make it real pretty, I'd have opposite of the quantity x plus y plus z all over w squared. And there's the first partial of f with respect to w. Cool. Let's do higher order partials and we'll wrap it up for today. But first, a mean. So here's a constant and her friend is the e to the x function. So the constant is all scared. Oh no, there comes differentiation. You know, because when you take a derivative of a constant, it goes to 0. So she's scared. And so the e to the x says, so what? You know, I'm a constant, it's going to eliminate me. And the e to the x is like, oh. So then the e to the x is like, I'm e to the x. Stay with me and I'll protect you from differentiation. So, you know, when you take the derivative of c e to the x, the c isn't going to get sent to 0 now because, you know, constant multiple rule. So the e to the x says, as long as you're with me, baby, differentiation can't eliminate you.
Oh, that's a good ending. That's a good ending.
But what happens if you take the derivative with respect to y of c e to the x? That whole thing goes to 0, right? I thought you would enjoy that, folks.
I did enjoy it. I did enjoy
Time
it.
to smile. Good, good. Thank you. Smile a little bit. It's Monday. Okay, higher order partials. So what do you know about higher order stuff? Let's do a quick Calc 1 review. You know that if somebody gives you a function y equals f of x, he's got a first derivative, you know, f prime. But doesn't he have higher order derivatives like f double prime, you know, f triple prime, et cetera, et cetera? You've seen that before, right? So in the world of partial differentiation, we also have higher order derivatives. So let's go with second partials first, and then we'll get to third and whatever. Okay, so let's do the notation first. When you have your df dx, and then somebody says, well, I want you to take the derivative of that with respect to x. It looks like d squared f over dx squared. And again, those d's have curvy stems. And yes, it matters, curvy stems. That's one way to say, go find the first partial of f, the second partial of f with respect to x, then with respect to x. And since you had to do it with respect to x both times, the other way to denote it using subscript notation is fxx, which is actually my personal favorite. I prefer that. What about if you take the partial with respect to y of df dy? D squared f over dy squared, or fyy. What if you have df dx? So you did that first, that's your first partial. But somebody says, well, I want you to take the derivative of that with respect to y. That looks like d squared f over dy dx, or fxy. And so the first letter says what happens first. This is very important that you get the order. And then you do the second letter, okay? And then ddx of df dy would look like d squared f over dx dy, and that would look like fyx. So in the world of diagrams here, because I'm a diagram kind of girl, I like these tree diagrams, you've got a couple of first partials, which you could denote zx, or you could denote it fx, and the other one is zy or fy. And then this first partial has two kids himself. His two kids are fxx and fxy. The other first partial has two second partials, or two kids. He's got fyx and fyy. So you have 4 grandkids total. What does that mean? That means that you have 4 second partial derivatives total. I know, it gets complicated. Yeah. Now, the last two second partials that we did here, the fxy and the fyx, those guys have a special name because those are like the mixed up kids. Those are called mixed partials. Yep, mixed partials. Let's do an example where we find all of the second partial derivatives for this cute little polynomial function, okay? That means we got to get all four, people. So in order to get the second partials, you have to go get the first partials first. So let's do that, whoa, real fast here. So let's go get fx and fy. So fx, don't forget, you're going to hold y constant. I'm going to go a little quickly now. The derivative of 3xy squared with respect to x is 3y squared. The derivative of minus 2y with respect to x is 0 because there's no factors of x in it, so it looks like a pure number, plus then the derivative of 5x squared y squared. The y squared is going to go along for the ride. When you differentiate 5x squared, you get 10x, so 10xy squared. And we're done with getting the first partial of f with respect to y. Let's go get the other first partial. Now we're going to take a derivative with respect to y. Don't forget to hold x constant. So the first term, the derivative of 3xy squared, with respect to y, you're going to have the 2y in there, and I'm going to multiply the 2 and the 3, so I'll have 6xy. The derivative of minus 2y with respect to y is minus 2, plus, and then when you differentiate 5x squared y squared, with respect to y, the 5x squared goes along for the ride. Multiply that by y squared's derivative, which is 2y, and you'll ultimately get 10x squared y. So there's the other first partial. Okay, so now what? Well, now we got to get all four of the grandkids here. Oh boy, here we go. fxx. fxx is the derivative of fx with respect to x. So you're going to again hold y constant, and the derivative of 3y squared is 0, so that's gone. And the derivative of 10xy squared with respect to x is 10y squared. So we're just going to get 10y squared there. Then his other kid, fxy, we're again going to look at fx, but we're going to take his derivative with respect to y. So the derivative of 3y squared with respect to y is 6y, and the derivative of 10xy squared with respect to y is 20xy. Okay, we got those two grandkids, and now we got two more. So now let's go get fyy. Fyy is the derivative of fy with respect to y. So you're going to go, okay, what's the derivative of 6xy with respect to y? 6x. And then the derivative of minus 2 is 0. And then the derivative of 10x squared with respect to y is 10x squared. And then last, the other mixed partial, fyx, you're going to take fy, look at him again, but take his derivative with respect to x. So 6xy's derivative with respect to y, with respect to x is 6y, and then the derivative of minus 2, of course, goes to 0. And then the derivative of 10x squared y with respect to x, you're going to get 20xy. Now, here's the part that I want you to look at here with your eyes. What happens with these mixed partials? Compare these two guys for me. How do fxy and fyx compare?
They're the same.
They're equal.
Very good. So that brings me to the next beautiful theorem, the equality of mixed partial derivatives theorem. If you have a function of x and y, and fxy and fyx are both continuous on an open disk R, that's like a little R neighborhood there, then for every point xy in that region, fxy will be equal to fyx. Pretty cool, huh? And now my grand finale. In the grand finale, we're going to be getting ordered, or we're going to get higher order partials. We're going to get not just second partials, third partials. What? Yeah. So it's kind of fun. So in this process, we're going to show that these two mixed partials, fxz and fzx, are equivalent, as they should be. And then we're also going to show that boy, this script, fxzz is going to give me the same as fzxz, which is the same as fzzx. These are third partials, okay? Third partials. And my eyeballs, oh boy, that's such tiny script, I can't even read it. Oh, better. Okay. Now you have to be careful. These fxzz and zxz and zzx, the reason why those are going to be equivalent is because z is in there twice and x is only in there once. This would not be equal to, for example, fxzx, because even though fxzx would be a wonderful third partial, it would not be equivalent to one of these third partials because we took the derivative with respect to x twice and z only once. So be careful, because I've put that on a true-false question in the past, and I've had people mess that up because they're still not clear on the exact mixed partial equivalency there. Okay, so we have a function of 3 variables here. Oh my God. So how many first partials does he have? 3. But I'm only going to get 2 to start because I only need the 2 to start. I only need fx and fz here because they're asking me to show fxz is the same as fzx. So fx, that means take the derivative with respect to x. Okay, so the very first term, when you differentiate y e to the x with respect to x, that's just going to be y e to the x. Because the derivative of e to the x is e to the x. Plus the derivative of x ln z with respect to x, since z is a constant, ln z is just a constant multiple there. So you just bring it along for the ride. Fine, I'm done with fx. Now let's go get another first partial, fz. That means you're going to hold y and x constant. So the derivative of y e to the x with respect to z is 0 because there's no z's in there. Plus the derivative of x ln z, well, x is a constant multiple, so copy it down. The derivative of ln of z is 1 over z. So this fz is simply x over z. Now we're ready to show this is true by getting the first partial. So fxz is the derivative of fx with respect to z. So we're first going to get a 0 there because the derivative of y e to the x with respect to z is 0, plus the derivative of ln of z with respect to z is 1 over z. So this second partial is just going to be 1 over z. Cool. Now let's get fzx. So fzx is obtained by getting your fz, which we have, it's x over z, and taking his derivative with respect to x. Well, when you're taking the derivative with respect to x, you hold z and y, although y isn't showing up in this, constant. So the derivative of x over z is just going to be 1 over z. And we're done. And do you see that these are the same as they should be? So we just showed that's true. And we're halfway there. Now we just have to show that all 3 of these third partials are equivalent. Oh my God. Okay. Third partials, baby. Let's do the fxzz because we can. fxzz is just the derivative of xz, which we got already. It's him. And you're going to differentiate with respect to z. I'm going to rewrite 1 over z as z to the negative 1 so I can use the power rule. So when I differentiate z to the negative 1, it's negative 1 z to the negative 2. And I'll rewrite that using positive exponents because it looks pretty. So there's that third partial. So save that for later. Now let's go get fzxz. Well, fzxz is fzx, which we got, his derivative with respect to z. But didn't we already do this? It's also going to be negative 1 over z squared. So far, these guys are the same as they should be. But what about that last guy, fzzx? So what we're going to need to do is we have to go get fzz first because we never got fzz. So fzz is the derivative of fz with respect to z. So if I rewrite fz as xz to the negative 1, and then I take the derivative of xz to the negative 1 with respect to z, x looks like a constant multiple, so copy it down for the right. And then we have negative 1 z to the negative 2 there. I'll rewrite this a little bit nicer. There's fzz. And now I can go get fzzx, which means take the derivative of fzz with respect to x. That means hold z constant. But this is just going to be negative z to the negative 2. And that's the same as negative 1 over z squared. So these are all the same as they should be, okay? Because, you know, those third partials are all mixed partials and they're equivalent, okay? And this is just some silly stuff. Okay. So congratulations, you now know what partial derivatives are. Yay!